I recorded one clip for one of my classes. It's an hour and 20-minute clip. This is one of those hybrid classes where I'm supposed to have online lecture. So I recorded 1 hour and 20 minutes of online lecture to distribute to my class. Except I forgot to switch the mic channel and it's all silent. So I had to go back and do it again. So that was a little painful.
You should have a checklist.
Yep. I should have a checklist. Yep. Well, you know the saying, stupid should hurt, careless should too. So that you don't do it again. That's the whole point. All right. So I'm going to get started. But before I get started, just have a few points to make. Sometimes when I see two submissions of homework assignments that are identical, and the kind of mistake made is really kind of unique, I will give 0 points to those people until I hear from those people to explain to me, okay, what happened, or well, I do not know that person, I have not worked with that person before, or something like that. By default, when I see something that is suspicious, I'll give those people a score of 0 until I hear from those people, and have some kind of explanation. Now I understand, in some of the homework assignments, half of the class were wrong exactly the same way, okay? But in those cases, that means that those kinds of mistakes is common, and most people make the same common mistake. But when only 2 people in the class make exactly the same mistake, the combination of mistakes, then it gets a little bit more suspicious, and I need to hear from the students either by email or in person in order to determine what just happened. So that's the first thing. Second thing has to do with can someone turn in quote unquote turn in homework assignments before the due date, have me to check everything, and then reply back to that person and say your homework is perfect, now go ahead and turn it in. The question is, is it reasonable to do that or not? So what are your thoughts? It's a class. It's reasonable?
I'll do it if it's reasonable.
Well, just program to check it and respond.
Well, I think it is.
It's extra work on your side.
It's extra work on my side, but I have to grade the homework assignment once anyway, right? So instead of making it more work, what I can do is to say, well, if you turn it in now, if you let me grade it now, then that's your score that you're getting. Okay? I don't really. It's hard to. I'm trying to find a good way, a nice way to put it. Other than I'm lazy and I don't want to do extra work. Because if a class like this with 50 people and each person turns it in before the due date and asks me, is this the answer? Can you give me an idea of whether I did it correctly or not? I cannot do it. That's just not enough time to do it. But if 1 or 2 people, ask me that question, yes, I can do it with a few people, 1 or 2. But I think I have to, have a policy of, if people ask me specific questions, I can answer specific questions. But they cannot turn in like a whole homework and say, okay, can you tell me, whether this is right or not? I think you guys should have a pretty good idea of whether it is all correct or not. You can ask me about certain things, like, if look at step 2, okay? Am I supposed to use, is this the correct way to apply the substitution rule? Okay, that is a very specific question, and I think, answering that question is fair and square. On the other hand, turning in something complete, and say, am I going to get all the points? I think that's a little bit too much. So for now, I'm just going to keep an eye on it, but I really, it's becoming a pattern, with certain people, so I just want to kind of think about it and let you guys know. All right, this is the homework assignment, and you can tell the number of people who turn in homework assignment has dropped dramatically.
Wow.
Enrollment of the class has not changed. No one has dropped yet. The class still has 51 students. But the number of submissions has changed from the usual about 47, 48 to 37. Yep.
How can we tell if we submitted if it went through, or is there any way to double check?
Yes, if you turn in, right after you turn in, Moodle will actually give you a link so they can download your own homework assignment back.
Really?
Yeah. Yeah, but that only happens after, that happens before it is due. I don't know for sure. I can log in as one of you and check whether that's still working or not. Go ahead.
On the left side, if you click the assignment tab, it'll actually tell you when you submitted the homework.
There you go. So that's a really good confirmation. Can you still download the file that you turn in?
If you click on the homework assignment, you can.
Okay, so that's a very good confirmation. Not only do you know when you turn it in, but you can also know what you turn in at that time. So yes, the answer is yes, you can double check whether you turned in something, and not only whether you turn it in, you can also tell what you turn in.
Can we turn in another one if we look at it?
Yes, as long as it is before the due date, of the homework assignment, you can turn in as many times as you want. But I can only grade the last one that you turn in because Moodle overwrites all the previous versions. So let me just go ahead and let you guys sign this form. So I'll start over here. And we'll work on this homework assignment. Okay? All right, the homework assignment only has 3 lines, and we have to find out the pre and post conditions. So what I'll do is I'm going to use a text editor, like mouse pad, and work on it. So I'll just go ahead and repeat the pseudocode first. All right, so there we go. So now we don't have to refer to the notes anymore. All right, oh, there's one more thing. I need to know the precondition because otherwise there's no way to work on it. Okay, so the precondition is already stated there. We'll paste it here. Any questions at this point? No questions? Now from past semesters, I know some people will get points dinged already at this point because somebody, I don't know who, but someone's going to say pre-1 is true. Okay, just because sometimes in the class I use true as the precondition doesn't mean that in this case true is the precondition, for line 1. So you have to read the question carefully. If the question tells you exactly what pre-1 is, you have to start with that precondition. Okay? So we'll go ahead and work on this. Okay? We want to work with line 1 first. With assignment statements, there are only 2 choices. You can either use the forget rule or you can use the substitution rule. To determine which way to go, you have to ask yourself potentially up to 2 questions. The first question usually is enough to tell you, which way you have to go. What is the first question? Exactly. Does the right-hand side refer to the left-hand side? In this case, no. Okay. If the answer is no to that question, you have to use the forget rule. There's no other way to do this. Okay. Yep.
You say we have to use false.
Say again?
We have to use false instead of no.
Oh, okay.
I mean,
Well, because I asked does.
Oh.
Okay. So if you want true or not, then is it true or false? That. How's that? Oh, true or false.
Does it work if we include like line 1 and we just put line 1 and then have the question next to it so we know what we're referring to?
At the right hand side, you mean here?
No, like at the very beginning in front of is. I just
Right
do
here?
like 1,
Okay.
X gets Z, and then I ask the question.
From the context, if it is clear that you're only referring to line 1, it's okay. But I will still be looking for the reason why you choose the forget rule instead of the sub rule. So as long as the reason is still stated,
Yeah, it's just to the right.
Yeah, that would be fine. Yeah. Okay, so we have to use the forget rule. So when we use the forget rule, we relate the post condition to the precondition using the forget operation. So we have to use a forget operation And what exactly are we forgetting in pre-1? Anything that mentions the left-hand side, which is x in this case. But we can also state something for sure after this, and that would be x equals z. That's correct. And from past semesters, somebody is going to say that. And that would not be acceptable. Okay? We talked about this in the class and said, and I mentioned why this is not acceptable, because we are not specifying what to do. When you see x gets z, that specifies what we are doing. We evaluate the right-hand side, and we make the left-hand side the same as the right-hand side. But in this case, it's a pre and post condition thing. We are making a statement. Are they the same or not? And when we are saying are they the same or not, then you have to use the equal symbol. So the left arrow symbol is not acceptable in this place. Okay. So I just want to point out the common mistakes. Even before I grade it, I know what the common mistakes are from past semesters. Now it is entirely possible that this is a super class and nobody makes these common mistakes, which is good. I'll be very happy if that is the case. The next line is just going to expand pre-1, and I'm assuming that most of you actually use an editor of some sort to work on this. Did anyone work on this using a napkin and they just scan the napkin? No? Well, it's possible. Scan the napkin, go through OCR, and turn it into a text file. Should have done that.
I did write it out on paper first.
Oh, well. Okay, so now we just plug in the actual pre-1 into the forget operation, and next we have to carry out the actual forget operation. This part does not refer to x, this part does refer to x, and this part does not refer to x. So we have to throw away this part and keep the other two. So z equals y is kept, z is different from v is kept, and then x equals to z is something that we add because of the assignment statement. Are there any questions at this point? Yep.
But now that x and z equals y, that would mean x equals y too.
Exactly, but you do not need to infer that from this.
What if I did?
That's fine. No points is taken. If you're extending the statements. But there's no need to do it, okay? As long as you carry out the forget operation mechanically, that's all that I'm looking for. Yep.
Do you care where to put parentheses? Like, do you care where to put the parentheses? Like,
The parentheses in this
yeah,
case?
before, z equals y, and then there's a parenthesis before and after z not equals b, and parenthesis again.
On which line?
Since
Which line are we talking about?
13.
On line 13?
Since line 12, you have forget parentheses. Should we like double parentheses that, or you know what I mean?
Did I make a mistake with my nesting of the parentheses?
No, I was saying like on the line 13.
On line 13?
Like put parentheses before z equals y, like parentheses z equals y, and parentheses whatever.
In this case, it is clear to me that if you do not have the parentheses, it is still clear to me what you mean, so
Doesn't matter
it's still
because they're all
okay.
and, right?
Right, because you still have comparisons that will be done first, and then the and will be done after that. So it's as long as it is clear, it's okay.
Oh.
Yep. All right, so post 1 is done, and now we need to start with pre-2. So pre-2 is not given to you. Pre-2 is the same as post 1 because line 2 follows line 1, or because they are sequential. Any way you want to state it is okay, as long as it is clear that you explain it somehow that pre-2 equals post 1. Okay. There are cases where pre-2 does not equal to post 1. Because statements, even though they are right after one is right after another, they are not sequential. Okay, like in the case of a conditional statement, the then portion, even though it is textually speaking, it is after the if part, you don't follow it because they're sequential. So in this case, they are sequential, and this is how one way to say it. You can say they're sequential. There are different ways to say it. Okay, now we have to figure out what is post 2. So once again, line 2 is an assignment statement. So with an assignment statement, we have to ask those two questions to determine which rule to use. And if you use an editor, you can just copy and paste the question, just change the line number, and also change the answer here. So if the answer is true, the right-hand side does refer to the left-hand side, then you have to find the inverse function. Yep.
For pre-1 equals the post one, don't you write out post one?
Sorry?
Don't you write out post one? So like after you do the pre-2, then don't you also put equal and then equals, you write out the rest
You don't
of it?
have to, because we already know what post 1 is. So if you write it out, that's good. If you don't, it's fine. We just have to establish the relationship between pre-2 and post 1 and explain why they are related. Yep. Okay, so now we are moving on to this part here. So in this case, f of x is going to be x plus 2. You don't have to use the letter f to refer to the function. If you want to use f, g, h, and so on, that's fine too. But you do have to tell me what is the inverse function of that. X minus 2, very good. Okay. So then you have to say, this is enough to tell me that an inverse function exists. If you want to state it explicitly, that's good. But just showing me that there's an inverse function and what it is enough to tell me that there's an inverse function. And then we have to use the substitution rule. When you use the substitution rule, the template is like this, right? The template is the post condition is related to the pre-condition, but we have to apply the substitution operation. Sorry? Pre-1? Pre-2. Because we're working with line 2. And then we have to find occurrences of the variable on the left-hand side, which in this case is x, and replace each occurrence with f prime, the inverse function, applied to x. Like that. So that's the first step, which is just a template. The second step is to expand all these components. Pre-2 equals to post 1, and we know post 1 is this expression here, so we put it here. And then f prime of x is defined here, so we say it is x minus 2. I always use parentheses surrounding that so that the replacement operation will not change the order of operator precedence. And then we just have to carry out this operation. Z equals y has no mentioning of x, so there's no effect on it. Z does not equal to b has no mentioning of x either. And this one does have x mentioned. So the x is replaced by x minus 2, and then this whole thing equals to z. And that's the end of post 2. Any questions about this? Yep.
Can you say z plus 2 equals x?
If you state z plus 2 equals x, that's fine. They are equivalent. That's a if and only if kind of thing. Okay, very good. So we only have one more to go. Pre-3 equals to post 2. Once again, because line 3 follows line 1. It's line 2. There's a fly. I need someone to debug. So in this case, it's kind of nice because you can just go ahead and copy. For the most part, it's copy and paste because it is the same kind of format. You just have to change the line number. So that is it true or false that the right-hand side of line 3 refer to the left-hand side? The answer is true. And then you have to change this part too and use y minus 2 as the original function. And then use y plus 2 as the inverse function. Yes?
If on my homework I didn't write is it true or false, I didn't write those, do I get points off?
Yes.
But everything else is correct. Points off.
I don't care about the correctness. Well, I care about the correctness, but I also care why. Do you know why it is like that? It is a homework. It's the homework assignment actually says that you have to use the same convention that I used in the class, and this is what I did in the class. I can even tell you exactly when I talked about it. It's on the 13th, 42 minutes into the lecture. Yes, I watch my videos occasionally because some students come in and they ask me questions, and I locate that portion, so that so that I can tell that student, okay, if you want to watch the video again, this is where I started to talk about that, so that's helpful. I'm not gonna take all the points off, just some. Okay, use the substitution rule. So once again, you can copy and paste a little bit of what you had before, but then you have to make some changes. Okay, because we are dealing with variable y in this case, and not variable x anymore. And then we'll go ahead and just expand these items. There's no need to do simplifications for this class, because this is not an algebra class, and we are just mechanically doing the replacement in this case. So y plus 2 is over here. So now we have to do the actual substitution. Z equals y does have a y in it, so that y has to be changed to y plus 2. Z is different from v, has no mentioning of y. And then the last one also has no mentioning of y, so it is not modified. And that's it. That's your solution. It takes 33 lines. But I do have a lot of empty lines and some lines that does not need to be there. Any questions about this? No questions?
Can we do like, what's it called, another one? Like a quick one?
Do another quick
Like a
one?
similar one? Yeah. just a-
Sure. Let's do another one. We're gonna do another one, on Thursday anyway, because these questions will be in your first exam.
Oh.
Yep. But that's okay. We can do another one, just so that we have more exposure to it.
Okay.
We don't have to do a multi-line one. I mean, you can see the multi-line, version really has it. It makes it lengthier, but it doesn't change the complexity. Does everybody agree that in this case, the number of lines of assignment statements does not make it more complex, it just makes it more tedious. Because for each line, the precondition and the postcondition, they're still related either by the forget rule or the substitution rule. So I don't really have to use a multi-line example just to show, just to give you guys one more example. So we'll just use line 57, and it turns out to be x times 2 plus 1. Okay. I think we have seen something like this, so we'll just go ahead and try to figure out what to do with this one. Or we'll make it even more interesting. Okay. And I have to give you what is the precondition. So I'll have to supply the precondition and say pre-57 turns out to be y is greater than z and x is different from w. Okay. Just some random expressions here. So in order to determine which rule to apply, you still have to ask that question. Okay? Is it true or is it false that the right-hand side of line 3 refer to the left-hand side?
True.
It is true. Okay? So even though we have a mentioning of y and possibly many other variables on the right-hand side, it still mentions x. That's the key. If it does not mention x, then you have to use the forget rule for sure. But since it does mention x here, that means it is still self-referencing, and then we have to ask the second question. The second question is, okay, let me just move this up a little bit because I think people in the back may have problems reading this part. So there you go. So the second question is, if I make the function f the same as the right-hand side, in this case f of x equals to x times 2 plus y, can I find the inverse function to reverse that operation? The answer is yes, we can reverse that operation. When you reverse the operation, you have to reverse the application of the operators. In other words, in the original function, we apply the addition last. That means in the inverse function, you have to apply the inverse of addition first. Which means we are going to subtract first. So you have to say x minus y first, and then we apply the other one, which is the reverse of multiply by 2 is the multiplication of 0.5 or division by 2. You can use either way to represent it. Are we doing okay so far? Now, how do we know this is right? Yep, go ahead.
Use that little algebra thing to find the inverse, basically.
Yeah, well, okay, here's the thing. Okay, let me just kind of move this out of the way first.
Remember it, though.
You can basically look at this as, line 57A being x gets x times 2. And then you can say that, oh, maybe there's a second line, to this thing, x gets x plus y. Is everybody convinced that line 57 as one single line is equivalent to line 57A and line 57B combined?
Yeah.
Well, if you're convinced of that, can we find the inverse function of x times 2? X divided by 2. Can we find the inverse of x plus y is x minus y? But the operation is we have to do this first, and then we do this one. But when you reverse it, we have to undo line 57b first, and then we undo line 57a. So that's why when you reverse a function, you have to apply the operators in an opposite direction. Is that helping a little bit?
Can you show it how would you do that? So you got x minus y divided by 2. I just don't see how that would work.
You don't see how this is the same as that?
Well, how would you do it if you didn't think of it like that? For 57A, 57B, how would you do it? Would you put?
You plug in some numbers to help you.
You saw some numbers.
Yeah, just plug in a number plug in 17 for x and 5 for y. Then because there are only so many ways to combine the operations, right? So in this case, if you don't know exactly how to derive the inverse function, you can do it by trial and error.
Yeah, I mean, for algebra, it would be x equals y plus 2. Then you would switch the variables, and then that's what
Okay.
I'm saying. Is it the same as this?
If you really want to know the math part of it,
Yeah.
I can show you one.
Okay.
Okay, let's say we have a function h of x. And let's just say that function h of x is the combination of g applied to f applied to x. Since you asked.
Yeah.
Okay? All right. So the question is, if I know what is g prime of x, g is reversible, is reversible, has an inverse function, and f is inverse, has a reverse or has an inverse function, is reversible as well. So the question is, what exactly is h prime? Okay, that's the question. So what you need to do is you have to apply. After you apply g prime to this whole thing, you get f back. And then you apply f prime to that mess, and you get x back, right? So the bottom line is, okay, if you apply g prime to g of f of x, what do you get? You get f of x back. Is that right? Okay, so so what if you apply f prime to this mess? Then you apply f prime to f of x, and then you get x back. Is that okay? So what is this telling you? Is this telling you that h prime of x is the same as f prime applied to g prime applied to x? So if you look at the definition of h, which is applying g last, if you look at the function h, which applies g last, and you look at h prime, which applies f prime last, that shows you the whole concept of reversing the order of the function itself. So when you look at f, g, and h, you can actually relate it back to our question here. Because x times 2 is done first. That is basically our f. X plus y is done last. That's our g. So when you work on the inverse function, you have to apply the inverse in the opposite direction. I don't want to turn this into a math class because the math department will not be very happy about that. But since you asked, it's legitimate for me to answer that question. And later on, we'll talk about why are we going through all this stuff here? Why do we want to be able to walk backwards in a program? Because all this stuff here are mechanisms that allows you to execute a program in reverse. Okay? So the question is, why do we want to do that? And I'll answer those questions later. So let's see, let's finish this one here. So we'll just go ahead and say the post condition of line 57 is based on the substitution operation applied to the precondition of line 57. We are looking for occurrences of x and replace those occurrences with f prime of x. And then the next line just go ahead and expands everything. And since we are all using an editor to do this, it's fairly easy to do it. And even the last part, just copy and paste. And here we actually go ahead and apply the substitution. And for those of you who have access to a reasonable editor, what you can do is you can just copy and paste the text here, and then you can select this block here, go to search, specify replace, and actually do the substitution using in your editor instead of doing it by hand. I didn't say that you cannot do it. I did not suggest it, but I did not say you cannot do it either. So you just have to say we are replacing occurrences of x by x minus y, the whole thing divided by 2. And the extra parentheses, make sure that I don't mess up the order of operation. And I just go ahead and say find and replace. And I'm hoping that it will only replace this portion. We'll see. Ah! No! 50 replacements, that cannot be right. Undo. Okay, well, you know, it will work well if you have a fancy editor that will allow you to do the search and replace only within the selected text. Okay, you know, in this case, I don't have a fancy editor like that. Fine. I'll do it the hard way. So hard. Okay, so that's another example of using the pre and post, deriving the post condition from the precondition with an assignment statement. Okay, any other questions?
So this is what would this be called? This is just not tracing, but
it's pre and post conditions. It's actually, technically speaking, it's called program verification. You know, this is basically a step or a mechanism in program verification. You have the precondition. In other words, I can tell you something about how the variables relate to each other, and then you have the program. You go through these derivations, and you arrive to some post condition for the entire algorithm. The question is that the proper post condition? Yep.
So anywhere it said x in the pre, you just put in the inverse. That's what you're saying, right?
Correct. You replace x with f prime, which is the inverse function applied to x. This part is just a template. Okay, what you need to change is just the line number and potentially the variable and also potentially the function name. But the concept still applies. You're still replacing occurrences of the variable on the left-hand side on that line with the inverse function of the right-hand side applied to that variable. So that part does not change. Yep.
Just a quick question. Had the function been a different equation to an exponent, instead of saying x times 2, it was x to the power of...
Then you take the log of that. Yep.
Thank you.
Yep. So many mathematical functions have inverses, but then you have to be careful sometimes. For instance, when you're dealing with sine and cosine, then you have to be careful because they fold an infinite number of values into a much smaller range. So when you take the inverse of, when you take the arc sine of something, it only gives you a certain angle, but the actual answer is that angle plus n times 360 degrees because for every revolution it gives you the same value. Actually, it gives you the same value twice, for each revolution because it's a sine. So you have to be careful. But all the things that we talk about only has one unique, inverse. So we don't worry about that sort of thing. Any other questions? No other questions? Yep.
Could you repeat? Okay, replace x with f prime of x. You said on the left-hand side, right-hand side, like the actual jargon.
Okay, I can do that.
Just so I remember it.
And I'll do it this way. This is the variable on the left-hand side, and this is the inverse function of the right-hand side applied to the variable on the left-hand side. And now I'll use the typical. I'm drawing a picture using text. Like that. Does it look good enough?
Yeah.
Or do you want it to be like a little better like this? And nobody complains. I have heard one person, telling me that I cannot open the file. It just, appears kind of like all jumbled up. So does that mean that everybody know how to open up the text files that we capture in this class, or they don't care?
Not a problem.
It was done
Okay,
first, yeah.
you have to open it with WordPad
Yeah,
and
yeah,
not
yeah.
Notepad. Yeah. That problem has to do with DOS and Unix have a different way to encode end of line. In DOS, end of line is carriage return plus a line feed. In Unix, it is just a line feed character. On a Mac, it is just the carriage return. So if you open it on a Mac, it may give you something entirely different. But WordPad knows how to deal with it, and you can also download a free programmer's notepad or programmer's editor, and most of those can self-detect what type of text file it is and open it correctly.
Like
Notepad++. Yep, Notepad++ is a good one. Yep. Yep.
Actually, line 57, right?
Line, sorry?
Line 41.
Line 40?
Actually 57, right? It says line.
You got to change line 3
Change line 3.
41.
on 41.
Line 41. Oh, okay, there you go. So that's the evil of copy and paste. And you will see that in programming it works the same way too. When you copy and paste code, you also end up with similar issues. Stuff that you carry over but should have been changed for this new place. Yeah. All right. Any other questions regarding these operations? Okay. So I will post the practice exam before Thursday. I'll do it as soon as I can. And you will see that some of those questions are related to what we have done, except you have to work your way backwards. Okay? And that's the whole idea. Well, that's not the whole idea, but the practical value of doing something like this is to have a good understanding of this stuff here and be able to execute a program backwards. I can show you some really simple cases without any proofs. Okay, so let's say that we have x gets x times 2, y gets 2 plus x. Okay, and let's just say that this is line 14, and this is line 15, and post 15. Okay, let's say in post 15 is we know y equals 16. Okay. And the program crashed at that point, okay? Or I know the program is doing something wrong at that point. So the question is, can I, without running the program again and set up breakpoints and stuff like that, can I go back and say, do I know the values of x and y before line 14, right before line 14?
Yeah.
Exactly. And we know how to do that because we know how to undo these operations. Now these will be fairly easy because if we know this y is 16, so x has to be 14. We know this x is 14, so we know this x has to be 7. Exactly. So why is it useful to be able to execute a program backwards? For debugging. Okay, when you write programs, there will be times your program does not do what it is supposed to. If you can execute a program in reverse, sometimes it will be very helpful because you know what leads the program down the wrong path. Okay, most of the time it is because of a wrong decision. It can be a loop exiting incorrectly. It can be the condition of a conditional statement, just being incorrect. So we'll deal with this on Thursday. There'll be more examples like this on Thursday. Any other questions about this? questions. So 40, yeah, go ahead.
So would you use an inverse or something, or we'll just do it on Thursday?
Yeah, on Thursday we'll go through questions from the sample test, which is the actual test 1 semester ago.
Okay.
So that's the exact test of exam 1 in spring 2011. Okay. So I'm not just making a simple test or an easy test. Those are the exact questions from last semester. All right. So this is all done. And we'll go back to the class because we have some unfinished business, don't we? You guys don't remember?
Top down.
Let's take a look at a file on last Thursday because we do have some unfinished business.
The brain teaser? What is it, the brain teaser?
That's the brain. Well, I cannot remember what the brain teaser was. What was the brain teaser? We'll find out. Now you know the true reason why I capture my notes and keep all my files up there, because I cannot remember. It's for my benefit. Okay, so the brain teaser.
Necessary conditions, sufficient and necessary.
That's you gotta go up.
I may not have a brain teaser, but I do have some unfinished business because this is not done yet. Okay, so let's reverse the time and go back to what we talked about last Thursday. Last Thursday, we looked at this particular conditional statement, and we know this one from way back when, okay? Because we talked about this when we talked about conditional statements to begin with. What does it do? Or what did I claim that it does? Yep.
Find the max.
Find the maximum of x and y and put it into z. Okay, so after this algorithm executes, z should be the maximum of x and y. We tested that. Okay, we used multiple traces to test with this one, and it works out in all cases. But the problem is, if I give you the next test case, what makes you think that it will work for the next test case also? Well, probably it will, but there's no guarantee. So we want to prove the correctness of this algorithm once and for all, and just say you can throw any value. X can be any value, y can be any value. I can guarantee that z will still be the maximum of the two. I want to be able to do that. And that's why we went through all the pre and post conditions, which is also to show you how to use pre and post conditions in the event of a conditional statement. When we're all done, the post condition looks like this. We look at this post condition and go like, well, that looks like it is correct. If x is greater than y and z equals x, or x is less than or equal to y and z equals y, seems to suggest that z is the maximum of the two. Okay, just intuitively speaking, it seems to make sense. And then what we did was to say, okay, if we don't look at the algorithm and just want to define what does it mean when z is the maximum of x and y, we started the discussion of using the imply operation. Okay, we started to talk about it in the form of x is greater than y implies z equals x, and x is less than y implies z equals y. And then we went through the whole big discussion of implies, implied by, and equivalent to. Okay, the if, only if, and if and only if. That's why we started to talk about that big mess. So the question now is this expression here equivalent to this expression? That was the remaining question. Do we know the algorithm is in fact correct? So what do you think? What can we do with this expression here? So let me just copy this portion to the notes for today. So let me close this and not save changes to this one. And go to the notes for today. Put it here. Okay, so the question is, what can we do with this? Well, this is kind of like a multiplication. This is kind of like an addition. Yep.
What's 87 saying?
87?
Line 87?
Line 87. Line 87 is changing the implied operator, so it becomes not something or something, not the conditional part or the consequence part. That is something that we talked about. Remember the truth table?
Okay.
So we proved that this is equivalent to that.
You're not saying that's the wrong answer. You're saying that's another way of saying the right answer with
Correct.
negatives.
Yes,
Okay.
it is just a syntactical change. We're just changing it from one form to the other.
Okay.
And then this one here, from this line to this line, we're just changing the comparison so that we get rid of the negation. Okay. So now I have to ask you this question. If I have A plus B times C plus D, what is that in arithmetics? Okay, so it's A times C plus B times C plus A times D, and then plus another B times C. BD, that's right. Okay, there we go. So basically it's a cross product. And guess what? It also works in Boolean logic. Okay, in other words, this expression here can become a much bigger mess. A much bigger mess looks like this. This becomes x is less than y, or x is greater than or equal to y. So I'm just combining this portion with this portion here. And I have to use multiple lines to do this because it's just going to be really messy if I use one line. X is less than y, or the other part, which is z equals y. Nope, I got it wrong. This is the or, that's the and. Okay, and then we have the other part, which is z equals x and greater than or equal to y, or let's see, one parenthesis. What is it? Z equals x and z equals y. There we go.
So the or is addition and the and is multiplication?
Yes. But it works the same way as this part here. Because you can see we combine the A and the C by the multiplication, and our so-called multiplication is our AND. Yep.
Not trying to confuse anybody, but what if on line 88, the second half of the AND, what if instead of or that was also an AND?
If this one is also an AND,
Would it just be one, would it be like x less than y and the rest of the statement?
well, if this is an AND, then you can apply the usual rules that apply to AND, which is commutative rule. Again, you can exchange the order, and also associative law, which means you can change the grouping of the parentheses. So it works the same way as a multiplication in normal arithmetics. Yep, go ahead.
Are you missing a parenthesis on line 89?
89, yep, missing this one here. Thank you. Yep.
Or is addition and is multiplication? Is that what?
Yes, they're kind of like that. Okay, so now we have, we just made it more messy than before, and the question is this going to work to our advantage? What is this? It looks kind of funky to me. Can someone give me a value for x and a value for y such that that conjunction is true? X is less than y and x is greater than or equal to y.
If they're both the same number.
Hmm?
If they're both the same number.
If they're both the same number, the conjunction will still be false because the first comparison is x is less than y. I need both sides to be true for the conjunction itself to be true. So the answer is no, can never be true, right? Regardless of the value of x and y, that's not true. Not true is false. Okay? That's fine. We'll just go ahead and say, this is false. It's not, there's no problem, converting something to false. And then we look at this and go like, well, it doesn't look like we can actually simplify this anymore. So we'll just stick it here the way it is, not a problem. And then we look at this one here, and then we ask the question: is there any way to simplify this? And the answer is no. There's no way to really simplify this. So we'll leave this one alone, like that. And then we look at the last part here. The last part is z equals x and z equals y. Well, we can definitely find cases where the conjunction is true, but is it generally true? If I don't tell you anything about x and y before the algorithm runs, can you guarantee that that is true all the time? No, you cannot, right? In fact, x and y, if they're different, then this conjunction will be false. So that means this is generally in general you cannot say it. Okay, so we cannot state it here, or in general for all values of x and y, it is actually false, because it's not true for all possible values of x and y. Okay, can we do something about this? False or something. Remember, or is kind of like addition, and false is kind of like 0. 0 plus something is something. Okay, because 0 is the identity for addition. So that means we can simplify this whole thing to really just this portion here. Now remember, I don't need you guys to do all the derivation, so don't get discouraged if you're not, you cannot work on the math. On the other hand, if I do the derivation, you should have a pretty good idea of how it works. There's a big difference between deriving this thing here versus understanding how it works. Is everything still making sense so far? Now, do we have the original thing back?
Yep.
Pretty close. I mean, the only case that is different is for the equal symbol. When x does equal to y, but that is that's easy to take care of. Because all we have to do is to change this part here. If we change this to that, that will make everything work exactly the way it's supposed to. So basically, we have just proved. Okay, now this is an important accomplishment, because at this point we have just proven the algorithm is correct, regardless of the values of x and y. I don't have to throw test cases at this algorithm anymore, because I know it is correct. Yep.
Is this what's called Boolean math or whatever? No.
This part here, all the derivation here, that's Boolean algebra, because it is kind of like what you do with regular algebra. To change the expressions, use the commutative law, use the associative law, use the distributive law, and so on and so forth, except it only applies to Boolean operators in this case, so it's called Boolean algebra. Yep.
For on line 87, when it goes to 88, so when you change the signs, why is it, it's like it says x is greater than or equal to y, then it changes to x is less than y. So why wouldn't it be x is less than or equal to, or no, not anymore?
The negation, the negation of x is greater than or equal to y is x is less than y.
So that's how it is.
Because
they
they
can't be equal to, that's why they could have changed.
Exactly, because they cannot be equal to, so it has to be less than. It cannot be less than or equal to.
So if you were to switch it, like if that right there, what you're highlighting was on in line 87, if you were to switch it, like say that,
like this?
Yeah. And
then it becomes
that. Oh, okay, okay.
Yep. They're flip sides of each other. Okay. Now I know the mechanical part of doing this is distracting, because there's a lot of symbols, a lot of stuff going on here, but the concept is more important. The concept is, now I just verify that this algorithm is correct. Okay, it's only a 5-line algorithm, but I can do it. I can prove that it is correct. So what if I can do the same thing to programs that are 20,000 lines long, 200,000 lines long, 2 million lines long? That means I can prove that a program is correct. I don't need to test it anymore. I don't need to throw things at it to see how it will, how it will respond to it. So if this can be automated, okay, if I can write a magic program to automate this process, I give it the algorithm as one input, I give it the precondition of the entire algorithm as another input, and it can give me the final result. Okay. What does that mean? That means even though if a program is faulty, I cannot tell where the fault is, I can at least tell that it is faulty. Okay? Which is one big step compared to what we have to do right now. What do you think Microsoft has to do before it releases, a new software? Like Windows 8.
Don't you mean should?
Huh?
Don't you mean should do?
Well, they released the beta version, but there's a reason why they released a beta version. Why do you think Microsoft released beta versions of software?
Because when you get the error, you send the report, they know where the error occurs.
Right.
They look at that
The
particular.
defects, right? So by trading off and say, okay, you can play with this really nice and cool Windows 8 with the Metro look, for free, you are becoming the guinea pig. You're working with it and you are testing it, and when it doesn't work, when it crashes, you will have to send a bug report back to Microsoft. So you are actually, as a beta tester, you are helping Microsoft to find out what is wrong with the software, so they have one last chance to fix it. Okay, and that's how we do things. I mean, Linux is the same way. I mean, Linux is open source. It does not, people do not make money, by selling, Linux, but it's the same thing. Okay, when you run into a problem, you have a bug report, and somebody will read the bug report and try to fix the problem. But we have to wait until the problem happens before we can do anything about the defect. If you can do this to Windows 8, to Microsoft Office, to LibreOffice, and complicated software like that, then you can actually release software that are 100% perfect.
Does that ever happen?
Well, this is called the holy grail of programming. And there's a reason why it's called a holy grail. So automated program verification is a part of the discipline called software engineering, and it's not a pipe dream, but it is a holy grail for computer scientists, because if we can do something like this to large programs and automate the process, then we don't have to worry about defects in software anymore. Okay. Any questions? So do you guys want to prove the correctness of every algorithm that we encounter in this class? No. Well, we are not quite done with pre and post conditions either, because we haven't done. You will do things about assignment statements and conditional statements. So you do have to go through the pre and post conditions, but only for assignment statements and conditional statements. But hold on a second here, Tech, you're forgetting something. There is a third type of statements that we have talked about already. What is it? Loops, right? So how come loops are not in the exam, in the scope of exams? Because it's really hard. That's why. So let's go ahead and move forward and talk about loops in this case. All right. Loops are not really that, horrible. I mean, you have, so let's just say that line 1 is while x is less than k, do. Line 2 says x gets x plus 1. Line 3 says and while. And we'll say pre1 is saying that, x has a value of, let's see, w. And we can sometimes even say that w is less than k. Okay, that's a good precondition there. We don't know what w is, but we do know that x starts with a value of w, and w is less than k, which means x is less than k to begin with. Okay, the question is, what is post 3?
X is
less
not
than K.
less than K.
No, x equals k. Okay?
Oh, yeah.
Now we know that because we have gone through a few traces with different test cases. Remember your loop homework assignment? Okay, so you know that if for certain types of things, for certain types of precondition, the post condition has to be a certain type too. But this is a very simple loop. With more complicated loops, can you apply a similar mechanism and prove to me what will happen after the loop executes? That's the big question. Well, let's work with this easy one first and see what we have to do to get to use pre and post conditions for loops. Okay. So we'll go ahead and just say that your pre1 is already given to us, and I'll ask you what is pre2. In other words, if I am about to execute line 2, what do we know?
X is less than K.
X is less than K.
Pre1.
Okay, we know that there's a chance that pre1 is still true. And what else do we know?
X is less than
Okay, but I'm leaving out something here. What else do we know? Remember, this is a loop. Hmm? Well, this part actually is a little bit hard to illustrate without a picture. So let's go ahead and draw a picture of this loop here. Okay, this is a loop. So with a loop, we come in from the top. But there's another way to merge into. I will finish this loop later. And then we branch. One branch goes all the way out of the algorithm. Another branch performs an operation. When the operation is done, we have to go back to the beginning and check the condition again. That's the general shape of a pre-checking loop. Pre-checking because we are asking the question to see which way to go before we perform the first operation. So in this case, we have the question of, is x less than k here? That's the question. If it is true, we go this way. If it is false, we go the other way. I have just given you pre1. Pre1 is what is true when you get past this point in this algorithm, right? The second question is, this is pre2. So the question is, what exactly is pre2? What do we know for sure when we are about to execute line 2?
Pre-1 or not pre-1?
Sorry?
The pre-1 is true or not?
Okay. Now we know the pre1 may be true. It may not be true, but it may be true. Because this may be the first time we get through here, so pre1 is one component. Yes?
Post 2.
Post 2, very good. Is that your answer too? Okay, very good. So you guys are recognizing post 2 is a part of pre2, as a component of pre2. Why is that? Because the other way to get back to this spot here is we have gone through at least one iteration, and we get through here. So that means pre1 may not be true anymore. But nonetheless, x still has to be less than k, and then we get back to this point. Because this is post 2. Post 2 is true all the way through this path, through the branch, and back to here. Don't we have a little bit of a problem now? Because the precondition depends on the very same post condition that it's supposed to get into. Okay? Okay, still you can say, well, that's okay, because line 2 is really just an assignment statement. It's a very simple one. The right-hand side refers to the left-hand side. There's an inverse function, so we can use the substitution rule. That is true. So we can say post 2 is based on the substitution. I'm skipping a few steps here. Based on the substitution of pre2, we replace occurrences of x by the inverse function applied to x, which in this case is x minus 1, because the original function is x plus 1, so the inverse function is x minus 1. And the second step is we replace pre2 with the actual stuff, which is this bunch here. 1. And we can do one more thing because we know what pre-1 is. So we can replace that pre-1 with that portion. I know this is a big mess. Okay, so pre-1 is this part here. Just stick it there. What is that? We have a problem here, don't we? We have a problem here because the result of the substitution depends on the result itself. Post 2 is both on the right-hand side and also inside the substitution here. Okay, but that's not where post 2 ends. Post 2 can be found somewhere else. Where else can you find post 2 as a component?
Post 3.
In post 3, okay, because post 2 is what is true here. So it goes around and gets back to this point, and at some point, x is less than k is going to be false, and then we get out to here. So when you look at post 3, which is at this point, what can we say about post 3? So we'll leave post 2 the way it is right now and just say that, well, that's kind of tricky. We don't know what to put. We don't know what a post 2 is. So let's work with post 3 first. What is post 3?
X is equal to k.
Okay. Well, that's the final answer. That's the final answer. But just from the structure of the loop here, what can we say about post 3?
We know that x is
There are
gonna
two
be-
ways to get there first. Okay. First of all, there are two ways to get there. There are two ways to get here in general, because we could have bypassed the loop altogether and get to the end the first time. This is just from the structure of a pre-checking loop and not in this specific case. Okay? In this specific case, it is not possible, but in general, that is one possible way. Is that okay? So what does that mean? That means pre-1 may still be true by the time you get to post 3. So we'll have to say pre-1 is one possible thing, but one thing has to be sure by the time we get to post 3, this condition has to be false. Okay, so we know that we can put the end not condition, so x is less than k has to be negated, has to be false. What is the other way to get here, other than branching all the way to the end without going into the loop points? It's the loop. Very good. So the other way is to go through the loop and then still decide to get out. And this branch, if you look at the green line, traces all the way back to here, which is our post 2. Okay, so post 2 is the other component that may be true when we get to post 3. So you can see how important post 2 is, because post 2 is needed to derive pre-2. It is by itself important, but it can also be true when we get out of the loop. And that's why post 2 has a special name. It is called a loop invariant. In other words, that condition does not change when you're spinning in the loop, or even after you exit the loop, it can still be true. It is called a loop invariant. So we'll go ahead and resolve post 3 as much as we can. Pre-1 is fairly easy, so we'll just stick that here. We don't know what post 2 is. And then the other one is just x is greater than or equal to k. Not x equals to k. We don't know that yet. We cannot derive that yet. Okay, so now we have, the big problem that we have to face at this point is somehow we have to pick a post 2 so that this equality has to hold true. Okay? So the question is, what can post 2 be so that this portion, the substitution operation, would get us back to the same thing that we start off with? And that's why it won't be in your first exam or the final exam, because finding the loop invariant is out of the scope of this class. This is not something that you can just mechanically derive. This is something that involves a little bit more analysis of the algorithm. In this case, we'll just say that, okay, let's say TAC claims that post2 is something really simple. Okay. I claim that. Okay. But one thing you will learn, not only from this class, but also from all the other classes that I teach, is you never trust TAC. Okay. Not that I want to lie to you and intentionally, be deceptive, but sometimes I just make, silly mistakes, careless mistakes, and that may not be true. So how do you know that that's true? Yep.
It's not necessarily true because if you do it enough times, it could be equal to k,
Okay.
thus exiting the loop or whatever that's called.
Kind of. But let's go ahead and plug in post2 being this mess here into this thing. Okay. So let me just restate the whole thing here. Okay. I'll just do some copy and paste. And the question is, if I say that post2 is x is less than or equal to k, can I still make this equality hold?
No.
So in this case, I don't have post2 anymore because I said that post2 is x is less than or equal to k. Okay. So you can see the question mark here because I'm saying that is this side of the equality the same as the left-hand side?
Yeah.
Well, it's a big mess. I mean, it's not obvious, is it? Okay, because we have a conjunction here in the inside, and then we have a disjunction on the outside. Okay. Well, let's try to figure this part out. Okay. So we'll go ahead and do the actual substitution, but this time I can actually go ahead and do the substitution because I don't have post2 here anymore. So we'll just go ahead and perform the substitution. Every time we see x, we replace it with x minus 1. And this is when it's really handy if I can do the substitution using the editor instead of doing it by hand. All right, so we'll just do it by hand. Yeah, that's fine. Do it by hand, and we'll do it by hand. Okay. That's a big mess. I mean, it's all right. So the question is, how do we solve this problem? Well, as it turns out, the distributive law in Boolean algebra works the other way too. In arithmetic, it does not. But in Boolean algebra, it also works the other way. In other words, in Boolean algebra, if I give you A and B or C, this is actually equivalent to A or C and A, B, or C. They turn out to be the same. Now this does not work in arithmetic, okay? When you replace and with multiplication and or with addition, it doesn't work in arithmetic, but it does work in Boolean logic. But TAC, how do you know this works? Well, you never trust TAC, remember. A, B, C, okay? So the way we prove this is using a truth table. How many cases do we have? How many combinations of A, B, and C can I generate when A, B, and C are all Boolean?
12.
No?
9.
8. 2 to the power of 3 is 8. Okay? So it goes like this. A can be true. A can be false. When A is true, B can be true. B can be false. When A is false, B can be true. B can be false. Are we doing okay so far? When A and B are both true, C can be true, or C can be false. When A is true and B is false, C can be true, C can be false. When A is false and B is true, C can be, guess what, true or false. When A is false and B is false, C can be true or false. I have just spelled out all possible input combinations into the equation. Is that right? This is a trick that you cannot do with arithmetics, with integer operations, because there's an infinite number of integers. But when you deal with Boolean values, there are only two. You can enumerate all possible cases. All right? So let's go ahead and evaluate this whole thing, A and B, the whole thing, or C. Well, if everything is true, we know it's true. In fact, we know that as long as C is true, the whole thing has to be true. So we'll deal with all the easy case first. Okay, whenever C is true, the whole thing has to be true. Okay, so we handle all the easy ones first. What about this one? A and B, the whole thing is using a conjunction, or C. A and B are both true, which means the conjunction is true. Well, or only needs one side to be true for the whole thing to be true. So this is already true. What about this one? False. It's false. What about this one? False. What about the last one? False. Okay. Does everybody understand how I derive this column of true-false values? I just plug in, A is true, B is true, C is true. What is this expression? A is true, B is true, C is false. What is that expression? Okay, well, let's move on to the next one. What about this one? Well, when everything is true, the whole thing has to be true. Well, what about this one? Is that true or is that false?
True.
It's true because inside there's an or, so that means as long as A or B is true, the whole thing has to be true. And in this case, this is true because A is true. In this case, this is true too because B is true, so the whole thing is true. And in fact, you can see that C is in both of those. So if C is true, we know the conjunction has to be true too. Is that working out okay? Because I'm just skipping a few steps here. If C is true, that guarantees that this disjunction is true. If C is true, it guarantees the disjunction is true. Then we end up with true and true again, which is also true. So that means I can apply the same trick. Whenever C is true, we know the whole expression has to be true. It's just a shortcut. I just want to handle all the easy cases first. What about this one? A is true, B is false, and C is false.
False.
The whole thing is false because B or C is going to be false. You only need one side to be false for the whole conjunction to be false. What about this one?
False.
It's the same thing. It's symmetric to the other one. And how about this one? It is false as well. So now, forget about the ABC column. Concentrate on this column and this column here. Do they match up exactly?
Yes.
For all rows? Well, if they match up the same for all rows, that means these two expressions are truly equivalent to each other. Every time you see something like this, you can simplify to this. Every time you see something like this, you can expand it to this. And that's what we are doing. That's what we're going to do here. And before we do something like that, let's do some, well, we're running out of time. But basically what we're going to do on Thursday is to go over the practice test, but we'll also go ahead and finish this so that I can show you. If you guys, okay, here's your brain teaser for those of you who want to have a brain teaser. The brain teaser is work with this one here so that it becomes the other side. Yep.
Is the test online? We're doing it online?
No, I cannot do the test online because the lab won't fit the whole class. Sorry?
Practice.
The practice test is going to be online. I will post a PDF online, and the PDF will contain the questions.
Okay.
Yeah. And if you're adding to the class, just come to me, right here, and I'll give you a permission number to add to the class. So I'm adding everybody who's on the wait list to the class at this point.
The roll sheet.
Yes, I have the roll sheet.
So we're talking
And I've been hiding it.
Thank you.
Wait,
Okay.